following presentation analyzes Video Lab Report number 4, Oscillations of a Spring Mass System. The objective of this lab had two primary components. First was our goal to compare the tracked position of the system during its oscillation against the computer's modeled oscillation prediction. Once this was accomplished, we had to determine if the energy principle was at work here in our system by determining the system's change in kinetic energy, change in gravitational potential energy, change in spring potential energy, and the change in total energy of the system. Through analysis of this lab, it was determined that the computational model better predicts the oscillation motion of the system, and also that the energy principle was indeed satisfied in the analyzed system. The following bits of information were either given or calculated before proceeding with the lab. The mass of the attached mass is equal to 0.402 kilograms. The initial time of observation is t equals 0 seconds. The initial position of the spring system is equal to negative 0.632 meters in the y direction. The time period between full oscillations is on average 1.615 seconds. The spring stiffness is equal to 6.085 Newton divided by meters, and its corresponding relaxed length is 0.0526 meters long. It should be noted that the following representation of the energy principle should hold constant for this experiment. Delta E is equal to 0 and is also equal to the sum of delta K, delta UG, and delta US. This is the major physics principle which governs the interactions of our spring mass system. Now that the parameters are set, it is time to begin analyzing the motion of our oscillating system. Note that the data table shows both t initial and the initial y position of the mass before the video clip begins. As the system oscillates, the motion is graphed at the top right of the screen. Tracker shows that our system oscillates completely 5 times during the 9.307 second stretch of analyzed motion. In order to determine the period between oscillations, one must average together the time changes between each oscillation. I measured the times of the first 4 complete oscillations, and when I averaged the delta t's together, calculated that delta t is equal to 1.615 seconds. This allowed me to calculate the spring stiffness, Ks, which is equal to 4 times pi squared divided by the quantity of the mass times the oscillation period. The spring stiffness, which I had determined, is equal to 6.085 newtons per meter. Using this spring stiffness, I was able to calculate L naught. In the system, the energy principle states that the negative of the gravitational potential energy is equal to the spring's potential energy because both delta K and delta E are equal to 0. L naught was determined to be equal to little g times the mass of the system divided by the spring stiffness. This was added to the spring's stretch length of 0.7 meters in order to calculate L naught equal to 0.0526 meters. The most important sections of the VPython code will now be discussed. First, one must set the mass of the object equal to 0.402 kilograms and the appropriate position of the spring equal to negative 0.632 meters. Next, the delta t time step must be set to the value much smaller than the time in between frames. As you recall, Ks is equal to 6.065 and L naught is equal to 0.0526. S is determined by the subtraction of L naught from the magnitude of L each time through the loop. The code shows that F net is equal to the sum of the spring force as the system oscillates and the gravitational force of the Earth, which constantly pulls at the system. Using Newton's second law, we can then update the velocity and position of the system in order to determine the spring's length as it changes during the period of oscillation. In the third section of code, I first determined that the kinetic energy of the system is equal to 1/2 mv squared. The gravitational potential energy of the system was determined by multiplying the mass of the system by little g by the y position of the system, which changes as the loop runs. Meanwhile, the spring's potential energy was equal to the product of 1/2 times Ks, the spring constant, and S squared. The change in each of these types of energies was determined by subtracting the previous energy type from the newly calculated type of energy. The following results are shown when VPython is run in order to compare Tracker's analysis of motion versus the computer's modeled motion. Note that the red line differs from the blue line based on human error used when tracking the system as it oscillates. The code is also capable of displaying all types of energy of the system. The red line graphs the spring's potential energy, while the green line graphs the gravitational potential energy of the system. The blue line graphs the kinetic energy of the system as it oscillates back and forth, and the yellow line, which is equal to delta E, is equal to 0 throughout the system, the sum of all the energies. Based on the graph which shows delta K, delta UG, delta US, and delta E, it can be said that the energy principle is satisfied in the system. The yellow line, which we recall is delta E, the sum of all the energies, is equal to 0 throughout the oscillation of the system. This satisfies the energy principle. When comparing the y displacement in time, it was determined that the period t is equal to 1.301 seconds between oscillations. Recall that the x period was equal to 1.615 seconds. Because ty is less than tx, it indicates that the oscillation achieves more displacement in the y direction as compared to the x direction displacement during the same t time period. Concluding remarks. It was shown that the VPython model more accurately displayed the oscillating motion of the spring mass system as compared to the raw data's oscillation motion. Remember, this may be attributed to incorrect analyzing techniques in Tracker. The lab also proved that the energy principle is both present and satisfied for the analyzed system. All initial energy is maintained without any loss to the environment, and the change in total energy was equal to 0. Thanks for watching.